postgraduate School of Computational Science, right? And we'll talk about something of cryptography. Please welcome.
Thank you for introductions, and I will talk about hardness and complexity in cryptography. Okay, first talk about what cryptographic hardness is and how to use it in cryptography, and we also talk about hardness versus complexity. And last, I introduced my research paper named Adventures in Crypto Matter: Attacks, Fixes, and Analysis of Weak random function. We'll focus on attacks for weak random function. And before start, we assume that P is not equal to NP. Since if P is equal to NP, then there are some strange cases in cryptography. For example, if someone in this seminar can prove that P is equal to NP, then right now most proof of the cryptography are meaningless, but they could still be secure because we don't know the direct attacks. So I assume that P is not equal to NP. Then let's start with hardness. In computer sciences, hardness roughly means NP hard. NP hard says that the NP hard problem is at least as hard as any NP problems, which means when you can solve an NP hard problem, then you can also solve any NP problem in polynomial time. So, moreover, NP hard gives the worst case complexity, which means that NP hard says that a specific problem is hard on some instances. On the other hand, in cryptography, it is well known that the security of cryptographic primitive is based on the cryptographic hardness. In these situations, we naturally have one question that are hardness in computer science and in cryptography the same? The answer is partially no, since cryptographic hardness requires different properties. Indeed, cryptographic hardness requires the average case complexity and reversibility, sometimes called the trapdoor. Average case complexity says that a specific problem is hard on most instances from some explicit distributions. So worst case complexity cannot guarantee the average case complexity. Moreover, cryptographic hardness also requires the reversibility. For example, we only know that an integer n is uniquely factorized into two large primes p and q, then it is also easy to multiply two large primes p and q to construct an integer n. However, multiplication of p and q is easy, but factorization of n is hard. So one way is easy, then other way is hard. So it is called the trapdoor. Okay, let's start the cryptographic hardness. Informally, cryptographic hardness is classified into two types. One is the computationally hard problem, and the other type is some special primitives such as random generators. As I said earlier, computationally hard problem requires average case complexity and reversibility. Moreover, it does not need NP hard. For example, factoring and discrete logarithm are well-known computationally hard problems, but many cryptographers believe that they are not NP hard. Since factoring and discrete logarithm are contained in NP class, and also they are contained in co-NP, so these problems are contained in NP and co-NP. If any problem in NP intersection co-NP is NP hard, then it includes MPs equal to co-MP. So, however, many cryptographers believe that they are not equal. Anyways, maybe factoring and discrete logarithm are not MP hard, maybe. However, they are widely used in cryptography more beyond. Yes. As a second type is some special primitives such as pseudo-random generators, which are they are secure against unknown attacks, and many cryptographers believe that some special primitives are secure, although there is no proof. It is kind of some strange, but it is reasonable. It is reasonable because if we can construct a pseudo-random generator without any assumptions, then we can show that P is not equal to MP. As an example, there is a Goldrich's random generator from expander graphs, and let's see it next slide. As an example, there are two examples, and one is a Goldrich 1A function, and the other example is Goldrich's pseudo-random generators. Let's see the function called TSA. A TSA function consists of summation of 3 bits and multiplication of 2 bits and their summations. So it looks simpler. Than for a simple function TSA, we can also define a new function called f like this. And the security of a 1A function is that it is hard to invert f. Here, invert means we cannot find the preimage of f in polynomial time. As another example, we can also construct a function g using TSA function many times. The security of pseudo-random generator is that if xi is random, then gx looks like a true random. As another example, I will introduce the Ramin's modular scaling 1A function. Fx is x squared modulo n, and the security of 1A function is the same as previous one. Unlike the previous two examples, there is a proof that inverting f is at least as hard as most n hard to factor. Here, most means average case complexity. Now we talk about how to use the cryptographic hardness in cryptography. Computational hard problem is used to construct a new cryptographic primitive. Indeed, we can construct a new scheme based on the hardness of computational hard problem, which means if someone can break our scheme, then someone can also solve the hardness problem in polynomial time. However, we already know the base problem is hard, so we can insist that our new primitive is secure. It is called a theory-driven approach because there is a proof. As an example, RC encryptions widely used in the real world, such as certificate for banking service or internet protocols, is based on the hardness of factoring. And moreover, OpenSSL and TLS protocols, they are also widely used in internet protocols. They are based on the hardness of discrete logarithm.
So could you remind me of how complex your factoring and is it number?
Sorry?
So what's the complexity, like best algorithms running time of factoring and bit number?
It is called the sub-exponential time complexity. We roughly say that roughly said it is the best algorithm for factoring problems. It's not exact, but yeah, roughly speaking.
So n is the number of bits.
Yes. Yeah. We call the polynomial time algorithm if the algorithm takes like this one. Yeah. Yeah. As an example. Yeah.
Constant in the tower. Zero, maybe.
And similarly, some secure primitive also based on the new cryptographic primitives. But as I always said, there is no proof. So it is called practice-oriented approach. They are secure against unknown attacks. As an example, if we have a random generators, then we can build the 1A function and encryption schemes. Moreover, a blockchain can be built from hash function plus super large alpha. Since the secret of a blockchain is quite complex, so there are many cryptographic primitives are contained in super large alpha, so we pass it right now. Yeah. Okay, now we discuss hardness versus concrete security. Yeah, it is the same as our title. Yeah, until now we know how to construct schemes based on the cryptographic hardness, and we want to instantiate the schemes in the real world. If there is a reduction from the cryptographic hardness, then the parameters of schemes must be set to follow the proof of reduction. However, no one does like this because we want to construct a more efficient cryptographic schemes. Indeed, concrete parameters are set to be secure against unknown attacks. So more intuitively, let's see the gray graph about parameters. When you use large parameters, then our scheme is more secure but less efficiency. On the other hand, when you use your small parameters, then our scheme is more efficient but less secure. Okay, and we assume that we have a security deduction, security proof, and we also have a text like blue and red area. When you use the parameters in blue area, then our scheme is secure, and when you use the parameters in red area, then our scheme is broken by attack. Then in this situation, current parameters is set as black coin. So which means we want more efficient scheme with tight security. So there is a gap between current parameters, concrete security, and hardness. To reduce the gap, we need to study attacks. Maybe I think attack is many mathematicians is good at cryptographic attacks. Yeah, I think. In this talk, I always notion attack as two types. First, attack is to solve computationally hard problem, and the second one is to break schemes directly. When you have a polynomial time attacks, then the conclusion is simple. We do not use the scheme anymore. However, when you have a algorithm which takes exponential time or sub-exponential time, then how to measure the security from the text? So a concept of lambda-based security was proposed. Lambda-based security means that unknown attacks cannot success in 2 to lambda time. More formally, lambda is set to logarithm of t over epsilon square for cost t and a success probability epsilon. In general, lambda is set as 128. So to design secure primitives, the construction of schemes become more complex, since designers usually add a random element to prevent unknown attacks. So, however, sometimes there is a non-trivial attack using algebraic relations, statistical leakage. So, after that, designers refix it again. So, when you have a attack and fix it, and there is a new attack and you also refix it again. So the concrete secret of cryptography is the cycle of attacks and fixes. However, sometimes there is a most primitive with no proof and no attacks, since it is too much complex. Trivial, it also has a low efficiency, so designers want simple constructions. It is so simplest construction is one of the crypto documentary, which means no one exploring here. So simplest constructions while preserving the hardness has several advantages, such as, for example, it is simple to describe and analyze, and it has a lower circuit complexity, and it has a good efficiency for various applications. We already saw a good example, coordinates 1A functions and random generator. They look simple, but maybe hard. Okay, now I'll introduce my paper, research paper, Adventures in Cryptography. This is a joint work with Jeong-Chun, Won-Hee Cho, and Jiseung Kim. Yeah. Okay, let's see definition of a mixed random function. X is an input space, and K is a secret space, and Y is an output space. A function F is called a mixed random function if, for a fixed K, anyone cannot distinguish two joint distributions whenever Xi is uniformly sampled from the finite set. Here, left arrow means an element is uniformly sampled from the finite set. There are many applications based on the hardness of mixed random function. Yeah. Okay, let's see the candidate of mixed random function in cryptography. X is an input and K is a secret key. Then Fk of X consists of inner product of input and secret key in modulo 2, and inner product of the same in modulo C and their summations. The secret key is the same as previous slide, which means fix a K, then anyone cannot distinguish two joint distributions whenever Xi's are sampled from the binary space. Current parameter is set as the n is 384, which means when you use this n, it is secure against unknown attacks. Moreover, I introduced a second candidate called Fa of X. Before start, we define a function map, which is the inner product of vector of ones and X in modulo 3. Then we can define Fa of X with a secret key A is a map of AX bracket 2. AX bracket 2 means that component-wise modulo 2 of a vector AX. Then for this candidate, n is set to 256. Both candidates use the mixture of linear computations over different moduli, so they have simple construction, and so it has low depth circuit complexity. It has a good efficiency for secure multi-party computations, and they are conjectured to satisfy exponential security. Since already there is a proof that impossibility of a low degree polynomial approximation, and any standard learning algorithm cannot break these candidates, which means they are secure against algebraic attacks. So what is exponential security? Exponential security is that any distinguisher with learning time 2 to the lambda cannot distinguish between two joint distributions even if we have exponentially many samples, but it's smaller than 2 to the lambda. So our goal is to distinguish two joint distributions when you have exponentially many samples. And in other words, when you have exponentially many samples, xi, omega I, then our goal is to determine omega I comes from y or not. Okay, let's see the first attack on fk of x. As I said, maybe it is secure against our algebraic attacks, so our basic strategy is to use a statistical difference between two joint distributions. Note that uniform distributions always output an element with 1/2 probability. So, we want to find some event called dot such that the difference is sufficiently larger than 1/2 to lambda. Since we have exponentially many samples, so when you can find such an event dot, then we can distinguish two joint distributions. So in other words, we want to find an event dot which is not contained in these intervals. Unfortunately, the basic event fk of x is 0 in modulo 2. The difference is smaller than 1/2 to the lambda, so in this case, we cannot distinguish two joint distributions. So we need to find another event. We easily observe that fk of x outputs 0 if inner product of x and k outputs 0, 1, and 2 in modulo 6. And it outputs 1 if the inner product outputs 3, 4, 5 in modulo 6. So we can regard input space of fk of x as the vector space in modulo 6. However, the actual input space is a binary space, so we want that it gives a statistical weakness. Indeed, our tag is extremely simple. The first distinguisher collects exponentially many samples xi and omega I such that omega I is always 0. Then for those samples, we can compute the conditional probability of xj is 0 given that omega is 0 for or j. Here xj is the jth component of vector x. If there is an index j such that the conditional probability is not contained in the interval, then we can conclude that omega I is an output of fk of x. Otherwise, we conclude omega I comes from the binary set. To support our tag holds, we can compute the we can compute the difference Pj from the straightforward but tedious computations. Therefore, we showed that a difference Pj is larger than 1/2 lambda for current parameters that lambda is 128 and n is equal to 384. The lemma shows that a conditional probability is occurring to h. Here h is the number of non-zero entries in a secret case. Then, as you can see, if h is 6k plus 2, then the conditional probability is exactly the same as the uniform distribution. So in this case, we need to find another event. It is also easy. It is also easy when it comes to the conditional probability of that xi and xj are both 0, but given that fk of x is 0 in modulo 2, we can observe that there is a biases from uniform distributions. So in summary, when you have exponentially many samples larger than 2 to the 0.21 n, we can show that we can distinguish two joint distributions, and a parameter n must be increased to 6.0 to be secure against our test. There is open questions since our tag requires exponentially many samples, so the secret of a weak random function fk of x with polynomially many samples remains an open problem. Okay, let's see the second attack. Our strategy is the same as previous attack. We want to use the statistical difference. So we can we want to find some event dot such that the difference is larger than 1/2 lambda. Okay, let's see the attacks. We first assume that A is a succulent matrix. A succulent matrix is a scalar matrix whose each row vector is rotated to one element to right, again. So a succulent matrix can be represented by the single vector. So succulent matrix is widely used in the cryptographic applications since the key size of the secret key size can be reduced from n squared to n. So it has a low communication cost, so it is more efficient than previous one. However, the security of mixed random functions with succulent matrix is considered as the same for randomly chosen A. Okay, before start, I'll introduce some interesting features of succulent matrices. Since succulent matrices, since each column vector of succulent matrices is the unique up to rotations, so the number of non-zero entries in each column vector of A is the same, called H. Then from H, vector of ones is the left eigenvalue of A with an eigenvector of A with an eigenvalue H. From this, we observed second equations and third equations. We also observed that we can also observe this. Moreover, if f(h) is x, which means the number of non-zero entries in a vector x is even, then we can also observe that H sub AX bracket 2 is also even. So the parity of AX bracket 2 is preserved whenever HX is even. Therefore, we observe that FA of X always outputs 0 or 2 whenever HX is even. This is a key observation of our attack. So our second attack is also simple. This is the almost same as previous attack. Yeah. First, the distinguishers collect many samples xi, omega I with such that hxi is even, i's are even. For those samples, we can compute the conditional probability, and we can conclude that the conditional probability is not contained. If the conditional probability is not contained in this interval, then we conclude that omega I is fa of xi. Otherwise, omega I is sampled from the G over 3G. Okay, let's see how our attack works well. Record that fa of x always outputs 0 or 2 whenever hx is even. So our goal is to compute the difference called p. And if p is sufficiently larger than 1 over 2t lambda, then we can break lambda bit security of fa of x. However, we cannot compute this conditional probability since ax bracket 2, each component of ax bracket 2 is not independent to each other. So we don't use any statistic tools, since almost the statistic tools requires the independent property. Yeah. Therefore, we heuristically assume that the difference p is close to q. Q is since y comes from the binary set, each component of y is independent to each other. So for current parameters, q is larger than 1 over 2t lambda. So we conclude that p is not in these intervals. We verify the assumptions by experiment result. I first introduced experiment result for several n. The y-axis is the logarithm of 1 over p. Our expectation is close to 2 to the 0.21 n. Then actual value is 0.2038, which is very similar to our expectations. So maybe our assumption works well in this from using this trend line. And we also run same experiment for a fixed n 18. Yeah. We run all possible cases of circulant matrix with a fixed n, which is the same as 2 to the 18. We run an experiment, and then we draw a graph. It is looking like a line, but it is actually a point. Since we have a lot of points, they look like a line. Yeah. The green points are follow our expectation, then moreover, we also find some irregular points drawn by red point. Indeed, there are 3.2% of irregular points that our attacks does not work in these cases. So for these cases, our assumption does not work well, so we need to overcome to find by finding some another event. Indeed, we can count the conditional probability is given that hx is odd instead of even, and when you draw a maximum size of two conditional distribution conditional probabilities, then we can observe that irregular points, red lines, are removed in the second graph. So we can still break the mixed random function. So in summary is also similar to previous attacks. If we have exponentially many samples, then we can break mixed random candidates under the current parameters. So the current n should be increased to 305. Moreover, the secret of mixed random function with polynomial in many samples is an open problem, and we also ask that is there a more powerful attack for these cases? Now I introduce some remark on our attacks. Since our attacks only requires conditional probabilities, so fully parallel computations are allowed, which means when you have delta processors, then total time complexity can be reduced from T sub total to this one. Yeah. Moreover, our attack can be extended to mode P, mode Q instead of mode 2 and mode 3 for arbitrary primes P and Q. Also, we note that if P and Q are larger, then they are more insecure. For example, when you use mode 3 over mode 5 with random function, then n should be increased to 4,000 for preserving lambda with security. Now I talk about how to fix the broken attacks and broken candidates without parameter increasing. The method is simple. When you add extra secret keys and copy the Peeling lemma. Peeling lemma says that the summation of two independent distributions defined on the binary set makes scaling biases. For example, X is distribution defined on binary set, and it has a bias P1, and Y is also a distribution defined on the same set, and it has P2 biases, and the summation of X plus Y has biases to P1 and P2. So using Peeling lemma, we can provide a new candidate called G, which consists of fk of x plus fk2 of x plus fk3 of x in modulo 2 is secure, which is secure against our attack. However, in this case, we cannot use the Peeling lemma directly since they are not independent of each other because they share a common input x. So we also, by running experimental results, we verified that G has biases, cubic biases, and Moreover, we can observe that the biases can be decreased exponentially according to L when you use the L secret keys. Similarly, we can prove the peeling of lemma defined on the ternary set, and for ternary set, peeling of lemma also says that the summation of two independent distributions makes scaling biases. So similarly, a new candidate H is also secure against our attack. From attacks and fixes, we can observe that the minimum number of vectors to represent a secret key, we denote it L, is a crucial factor of the security of weak random functions. For attack cases, succulent matrix A and vector K are both the case of arith 1, and our fixed candidate G and H are secure against our attack since they use 3 secret keys. So from these observations, we want to analyze the main candidate FA over X with randomly chosen matrix A, and our main question is this weak random function secure? And our answer is maybe yes. We cannot break them. Indeed, we observed that FA over X plus N can be represented by trace of some matrices. Moreover, for some matrices P, we showed that P of X plus Y is equal to P of X, P of Y in model 3, which means P is an input homomorphism. So using these observations, we provide a new analysis for random A. If X plus Y plus Z is equal to 0, then without loss of generality, we can assume that X plus Y is equal to Z. Then here, for such X plus X, Y, Z vectors, we can show that their summations can be represented by trace of Px plus Py plus P of X plus P of X, P of Y in modulo 3. So from the new relations, we can come to a difference between two joint distributions called PS. However, for any S, we cannot break current parameters of weak random functions. Indeed, if S is 2, then the difference is sufficiently larger than 1 over 2 to lambda, but it is outside of our setup. Moreover, for all cases, both results are contained in this interval, which means we cannot break current parameters. Moreover, finding such vectors such that summation of xi is 0 in modulo 2 is also well-known computationally hard problem called SXOR problems. Moreover, it takes exponential time and spaces. Therefore, we also conjectured that FA of X with random secret key might be exponential secure. The last slide, I introduced open questions in this talk, and I sorted them from strongest to weakest. The first first open question is the secret of Goldrich PRG. If we can solve it, then we can also solve P is not equal to NP. So it will be the rich man. And the second open question is the security of weak random functions with polynomially many samples. Our attacks must require exponential many samples, so for this case, it remains as an open problem. The last question is that a refined analysis on FA of X with random secret key A. Thank you for attention.
Questions? Any questions? Is there some? So it seems that like we are trying to sample some space and then compare that with the output of this function in order to guess the secret key, or
No, for this case, our goal is to distinguish two distributions that find such.
oh,
Yeah, that find a secret. Yeah.
But this is only a one kind of attack, right? There could be some other attack
Yeah.
which
Yes.
is unknown.
Yeah.
This is to guarantee that it's safe against this particular attack.
Yeah, to the particular. So when you find another text, then it could be increase the size of current parameters. Yeah. I think it looks very simple, so we don't know how to use the relations because there is no relations in this candidate. Yeah.
Any other?
You were talking about this average case complexity.
Yeah.
Is there good examples where that is really much faster than worst case?
Oh, as you know, TSP problem is well known that NP hard, but average case of the problem is more easy than worst case. Yeah.
It can be polynomial time even?
Yeah. No. The polynomial type, but the performance of algorithm is good. Yeah. For average case of TSP problem. Yes.
So what do you mean by average case of TSP? Do you mean random graph, or do you mean?
We fix the vertex of graphs and randomly chosen from graph from some fixed vertex of graph distributions. Then it is the algorithm is has a good performance in this case, better than expected one. Yeah.
Any other questions? So if not, let's thank the speaker.